you, Chris. My name is Robert Young. I'm a systems engineer at Mist, a wireless company recently acquired by Juniper. What I'd like to do over the next little while is avoid the echo. Is talk to you a little bit about, of course, wireless. Not just wireless, but maybe a little bit of context. The history of how it's been supported over time, things that can be challenging in supporting it, as well as the way that wireless, specifically Wi-Fi, has changed the way that we work. Now, the way that we're talking about things within the Ascension conference, I think AI is a big thing that everyone's talking about in machine learning. What I'd like to do is maybe give you a bit of an opinion from the field engineer's opinion of what AI really means, what machine learning really can do to help you create an automated, autonomous, self-driving network that allows you to stop focusing on troubleshooting networks and focus more importantly on innovation. Can you hear me okay in the back? Okay. So, transition to AI-driven networking. When we started back, many of us, many years ago, everything was connection-oriented. As Chris mentioned, I started on Tier 1 help desk. What we would do is log calls. We would assign them to specific resources. Tier 2 would then find out what specialists needed to be engaged. It was a very mechanical, very process-oriented mechanism. We treated the way that infrastructure was put together in the exact same way. There was no automation. You may have had certain things like automatic ticket generation, coming off traps, syslog, things like that. But for the most part, everything was completely manual. And the challenge with things being very manually process-oriented is it took a lot of time and you required very skilled resources that are very hard to get. Skilled resources that are also very hard to retain from an HR perspective. So what we really need to do to improve, make things better in the environment is to create proactive, predictive, and self-healing networks. Now that's a lot to say, and a lot of people are like, yeah, it's the same thing, everyone has AI-driven everything now. What I'm going to do today is talk maybe a little bit about definitions of what this means and how systems can be engineered to think like engineers that will actually create self-driving networks. Now there's two stats that I'd like to touch base on. First and foremost one has to do with budget. This is something that I've lived through many years. We also have many customers who have the same challenge. IDC and many other industry analysts say that 75% of your budget is spent just keeping the lights on. Keeping people, troubleshooting things, tracing tickets, diagnosing faults. That only leaves 25% for innovation. The concept of having proactive, predictive, and self-healing networks is to flip that ratio around so that the system is driving the bus for you. And what you're going to do is create new innovative things that engage external customers. How do you do that? A big part of that is understanding a lot of the definitions of what different things mean. I'll get into some of the plumbing details a bit later on because at the end of the day we're all plumbers. Network engineers are generally considered plumbers. But understanding the definitions of things, specifically artificial intelligence. Everybody talks about AI. What does it really mean from a practical perspective? AI is not walking over to an Alexa and telling it to do a very specific configuration thing. You can have a co-op student do that for you. There's not a lot of value in it. AI is having the system capable of taking inputs from you, watching the system like a trained team of network engineers. You're going to have an RF guy, you're going to have a switch guy, you're going to have a client guy, you're going to have a server guy. All of them running individual processes that actually thinks like the team that you need so that you can flip that ratio, 75-25, and spend most of your time creating new cool things. I'll also talk about the context of machine learning. Machine learning in the wireless world, I can use the example of radio resource management. You have a system that's been programmed to watch certain things. In this room, there'll be multiple access points. Each are watching the channel and power, the adjacent access points, the number of clients that are in the room. And there's going to be certain algorithms that teach the system to understand how to change itself to make things a little bit better. This is one of the fundamental things about Wi-Fi is handling spectrum. You can take that a little further up, where you have the concept of deep learning. RRM, or radio resource management, is pretty interesting. But when you get something that's a little more complex, and I'll use the example of a game of chess. You can have multiple players in a game of chess. Each of them are going to have specific moves, and there will be tactics that get reevaluated every single time a play has been made. That's where you get to the concept of something that's a little more like deep learning. And you can pull it all together using the concept of data science. You can have your subject matter specialist, someone who has the expertise of your LAN engineer, your RF engineer, your server guy, explaining how to take the information that you get from one data pool and combine it together, and from a practical perspective for the field guy, that's what AI will really mean, because then they can start doing things as opposed to just keeping the lights on. So I like this slide because over the years, what's wrong with the network? It sucks. Thanks. That's not very meaningful. Trying to understand what's actually happening in the environment is probably the most difficult thing as an engineer. And I'll give you a hint. Even though when you spin up your Linksys at home and Netflix works great, putting it into an enterprise with a NAC, with radius servers, with all sorts of different interLAN extensions, it's a heck of a lot more complicated than you may think. But you can make it easy. When I talked about understanding artificial intelligence and being able to process data, you need to get good data from the edge, and that starts with understanding how the system works. So first and foremost, you're going to have a radio link. Everyone's phone, for example, has a radio that's capable of 2.4 gigahertz and 5 gigahertz, as well as a Bluetooth radio. And it's going to talk to little access points that look like smoke detectors all over the place. Now, everyone from an engineering perspective in the old days said, okay, great, we're going to write our applications for copper, either 10100 copper or gate copper. Unfortunately, I'll tell you the dirty little secret about Wi-Fi. It's half duplex, and it's a shared media. It's like a hub. So if you've got one person that's being really bursty with traffic, and it doesn't play by the rules, everybody else in the network's going to have to back off. So if you've got people that are developing applications, your client devices may not understand how to communicate over that basic media. You don't have a copper or a fiber connection to these devices. So understanding what's happening with these client devices, every single aspect of the connection state. With us, we monitor over 150 different connection states per minute on the client, can give you the analytics. This draws back into getting data that can be put into machine learning, that can be put into deep learning algorithms that can be massaged by the data scientists to actually create a network that can drive itself. So, we've talked about RF, authentication and encryption. Again, people used to just plugging into copper. There's a whole bunch of different stuff that happens. Every single one of these packets needs to be encrypted and decrypted. There's a lot of different things that you need to monitor and understand if any of these states are failing. So I guess what I'm driving at is there's a lot going on. It's not easy. But if you understand and can monitor for deviations in any one of those connection states, you can start correlating stuff. I may have decryption packets. It's an error, but it's not actually causing my system to fail. That would be a false positive. We can cast them out with an intelligent system. Roaming and cell sizes. Another thing here has to do with the way that when you design an RF network, I've heard, AI is going to mean that I don't have to do a survey, not another survey. That's going to be great. Well, you can't argue with the law of physics. In this particular room, you're going to have redundant APs, and you have to design them such that if one of them fails, I can connect to the other one, and the client devices don't ping-pong back and forth between them. These are other things that you can monitor as part of your data collection. Which brings us to clients. This laptop has an enterprise chipset, has a nice big antenna in it. It can transmit, I believe, at 100 milliwatts. This phone, in a case, maybe does 12 milliwatts, a fraction of the transmit power that it's capable of putting out. When I design my RF networks, I have to balance the path from the AP to the client as well as from the client back. So when everyone says, oh, my APs can do 15,000 square feet, yeah, I can, but if you put a consumer device with a lousy radio in it, I can guarantee that half of your objects will fail to roam or are going to have a bad connection. This is the type of deep understanding of how these things have to be balanced, which you can build into your AI systems to understand and give you predictive analysis as to when things start to fail. And I'm actually going to show you some of this stuff in real time in a demo in a few minutes. Which brings us to power and receiver sensitivity. Not all devices are created evenly. One of the common problems we used to have, people run scan guns. Over the course of 5 years, they'd be dropped enough, the antennas break. Individual devices, even though they're consistent with regards to driver versions, you may have a golden image that you push out to them, each object, each physical client device may have failed, which means that when you start aggregating these buckets, what you have to do is say, okay, well, I've got a standard device type, and then check for deviations between that client device type. These are the types of data sets that you need to pull in the system. Because when it comes trying to troubleshoot these things, and typically what we do is, okay, go to the site, try to replicate it. It's very, very time consuming. Often you have to fly. Large warehouse, for example, you literally have to hop on a plane and fly out to Calgary. Been there, done that. Because you're trying to troubleshoot a device until the person realizes that the battery's been half dead for 6 months because someone didn't bother to spend the money to replace them. These are the types of variables that are going to impact your ability to deliver a successful system. It's the reason that you're spending that 75% of your budget troubleshooting networks. If you had a way to get information as to what exactly is broken, which one of those 150 plus data sets are actually triggering your fault. That's when you can go and analyze systems. Once you understand what's wrong, then you can start programming algorithms that will start automating it for you in the future, such that it says, you need to replace this device. I'm going to show you something in our demo as well, which shows that you're going to have to replace a specific AP that has faults, radio faults, Ethernet faults that haven't been resolved through replacing the cables. And environmental variables. So imagine that I'm on a Skype call, and I'm standing here, and the access point's right over there. I have a great connection, kind of like the microphone here. As soon as I turn my head the other way, I've got a big bag of water that's right between this radio and the access point. I've changed the environment that this client is seeing its radio connection. It's a layer 1 link to the network. Unless you can troubleshoot and diagnose that when I made a change, I've lost my signal by tracking very granular information. Remember I talked about connection states? Unless you can track the connection states with that level of detail, you can't say that, oh, I understand what's going wrong. Good examples where we have here, we rolled out a distribution center. It's about 1.5 million square feet. This is with a controller-based company. And along one section of the building, everything was perfect. It was actually near the loading docks. Lo and behold, 2 months later, the sprinkler guys came in and said, we have to put some additional drains up in the top. And they put an 8-inch cast iron pipe right along all of the access points and knocked RF in half the building. So even if you built excellent RF at one point, the RF environment changed enough that you lost connectivity. Now, without a baseline, it's very difficult to understand when these anomalies transpire. So it's great until Tuesday, and then things really suck on Tuesday. It gives you an idea that you should probably go check to see what was happening at the facility on the Tuesday. Another example of that would be HVAC, ducting, all these different types of things that happen in an office. Because if you have to send a person to the site to inspect before and afters, it becomes very expensive. This ties back into troubleshooting the network. That's why it takes so much time. Which boils into workplace changes. How many of you, when you first started working, sat in a cubicle? How many of you had a copper phone, wired phone? Yeah, same thing. Mine was Cat 3, actually, it was a while ago. Yeah, then most of us had a wired PC. Each of those cubicles took anywhere between 36 and 42 square feet of floor space in the environment. But then people started getting issued laptops, which was kind of cool, because you could take your work home, for better or for worse. More importantly, if you didn't want to go in on a Monday or go in on a Friday, you had that flexibility, which meant that office managers were noticing that cubicles were being unused. So what's an office manager going to look if I'm only using 8% occupancy on my cubes, and I've got 10 offices, I can probably close one of my offices. So there's been a very large financial driver within the facilities teams to say, get rid of the cubes, create what's called a hotel station. The hotel station, how many of you seen hotel stations? I think they're awesome. They're phenomenal ways to allow workers to have a positive work-life balance. You're not nailed in a cube. If you want to take a call, you can do it anywhere. The most important part as well is it enables a mobile workforce. When we sat at our cubicles back in the day, we'd have a PC. We might have a laptop, but we'd never run our work phone on this. I was issued a BlackBerry for many years because it was the most secure way to do it. But then as handset technology, the smartphone revolution transpired, what's happened is I can run all sorts of cool stuff, and this has become my desktop. I don't need it anymore. I can sit in a coffee shop or my hotel station, which allows me to sit perhaps 250 people on the floor as opposed to 50, a typical implementation. Now, then the IT folks look at it and say, well, that kind of sucks for me because I only had to worry about laptops before and I control the driver revisions and things like that and authentication. Now I have to worry about microsegmentation, onboarding all of these little handsets. Things got really complicated. So, you know, if it was busy before troubleshooting, we've added tremendous new layers of complexity as we're trying to innovate. And that's why when I started off the top, if there's ways that we can start automation, we can apply those resources to innovation so that you can roll out the cool stuff, because the people that really enjoy the work-life balance are internal customers. And those internal customers love innovation. Everyone likes a new app. Expenses, was just doing them yesterday. Things like that make your life easier, streamline things so you can ask resources to focus on tasks which are more important as opposed to busy work. Same thing applies in I did a lot of work in the retail space as well, and customer retention has always been a massive thing. Anyone who's shopped on Amazon knows that your local brick and mortar retailer would prefer that you didn't do that. So customer engagement, customer loyalty, There's new technologies with regards to Bluetooth notifications, location, wayfinding, all these cool little services can be layered on top of the system, but they're difficult to implement because everyone expects seamless connectivity. Oh, there we go. Because mission, back in the day, we'd implement Spectrum 24 RF guns in warehouses because the guy in receiving couldn't literally carry a tether over to his crates for doing receiving work. We would have RF cells, which are 15,000 square feet, because all I carried was just covering that one spot, and we'd have one AP. And if it went down, oh well, I'll receive it, I'll do the receiving a little bit later, as opposed to now, because we're running voice, video, and all our data apps, and people's expectations are one heck of a lot higher than they used to be. Wi-Fi now has to be mission critical. So how do you get around dealing with some of that? Part of that is understanding how we need to get from there to here. There was very mechanical. We started by implementing data analytics aggregation. What you need to do is understand what data points you get off your devices in the field. Now clearly when I say access point or AP, the AP is running code. The code is told to look for certain things, certain anomalies, certain variables, logs for the most part. Once you aggregate that, what you can do is create programs that know how to analyze this and start creating trends, basic baselines. Once you've got the baselines, what you can do is use your data scientists, leverage their ability to look into different containers, find relationships, and predict new outcomes, which are far more complex because it has far more data sets coming in. Which then brings us to things like what I'll call a virtual assistant, which I'll show you shortly. The virtual assistant allows a person that would typically be doing tier 1 to run standard, not CLI commands, standard text commands, show unhappy clients. You can find them for a site, for a location. I could search for a device. What that will allow you to do is tier 1. Can you tell me your name, please? What's your telephone number? What's your location? All this other stuff. What's your operating system? We'd never get out of that. Tier 2 would get it. What we can do, and the premise is that we're no longer focused on tier 1 activities or tier 2 activities. What we're doing is filtering the system's events such that we will automatically understand and be given a package which contains all the information we should need for basic diagnosis. And next step, of course, is the self-driving network. Now, we're not there yet. I don't think Tesla's allowed to let us hop in a car and have a nap and drive to Calgary and back. But as long as you've got the fundamental information, every single one of these elements builds on everything else. And the point being is, this takes time. And the hardware's never been along with us. And one of the reasons, people have had dreams about how this stuff will be happening for many years. Data scientists have been out there for a very long time. One of the challenges, though, is when wireless access points were deployed, they were typically deployed on a controller. There's a limited amount of RAM, limited amount of CPU, and limited backplane on these devices for compute. 7? So what I'm going to do is just flip through and say what's really driven a lot of this is self-learning networks and microsystems, microservice-based infrastructure. What I wanted to do, if I've got 7 minutes left, was actually show you some of this in action. There's a couple of slides that are going to be in the deck, which relate to some of the things that you need to do to make sure that you properly go through this logic, identify what's the problem, isolate the problem, analyze what's going on, verify what it is because they could be false positives, and then remedy the change. So I'm going to do a base demo here. I'm hoping, I apologize for that. I'll zoom that over. So what we're going to do here is take a look at a live system that we have in use. It would help if this was powered up. What I'm going to show you right now is a live demo environment that we have. The company Have This System's been around for about 4 years. It was recently acquired by Juniper. And what I'll show you is different things like an analytics baseline. Remember what I talked about a baseline? You don't know if it's broken unless you've got a baseline. All right. So what I'm going to dig in right here, imagine that I've got all these access points, monitoring clients, grabbing at least 150 data points per minute, aggregating in the system. I can then create trends. Trends that are important to the engineers, the type of things that they need to do to make decisions. How long does it take for the client to get on the network? What's their throughput? I talked about RF, roaming variables. Then you can break them down into different subsets, and the capacity I can look for interference. In this particular site, I know that I took a hit in interference at a certain point in time. These are the types of things, and all of this is API driven, can be used by your network engineers to go in and understand what's going on. Now, the reality is most people will not even look at this screen. Our larger customers who are doing very large deployments would actually use APIs to call in and snag this information and bring that into their NMSs. If there's a deviation from what the baseline needs to be, they would actually create a ticket that flows via additional automated measures into their ticketing systems. Same thing happens with the deployment. They don't go and configure stuff in the system, they'll just create scripts, and what they'll do is deploy them. In their particular instance, one of the last large deployment we did was about 45 out of 55,000 APs we deployed in less than about 6 months. So, and it's all automated, so the baselines start getting aggregated automatically. Things that I refer to otherwhere, so physical layer, forward path, reverse path, a whole bunch of different stuff that will help you troubleshoot this. More importantly, what it will do, and I'll pop right into the assistance engineer, is taking a look at things like actions. So this is another demo site where we've specifically gone in and broken a couple of things in it. So one of the nicest things about current open standards, that was on the first slide, is that you can talk to other devices using standard protocols. You're not locked in such that if I want to take advantage of the analytics technology, I then have to replace my switches, put a fabric server, a fabric client, and I have to put aggregation servers in a whole bunch of different boxes. Everything I'm showing you is cloud-based, and it's enabled with just one access point. What I can do at this point, I can dig in, I can find out switches that are missing VLANs. Anyone who's done a deployment understands that when you're in the field, somebody's going to potentially fat figure a switchboard trunk config, and it's incredibly difficult to troubleshoot. It may take you a week to understand it's a problem and do things like that. Bad cables, negotiation mismatch. A lot of this information can be learned right from the AP because it's watching client states. It's also watching its own interface states as well. So while this is our specific system, I believe the concept is that the devices you put in the network as a best-in-breed overlay should be able to aggregate enough information and feed it into a backend system that the AI teams can pull out meaningful information. And that meaningful information could be looked at by anyone who's clicking through, and I'm looking at a site and what's wrong with it. I'm also having AP authentication failures. This particular thing, if I scroll down, will actually show you the server and when it actually had a fault. Anyone who's had to parse large radius server logs will understand that it's incredibly difficult to do. Here, it can be done in a matter of seconds. The point being, and I'll just do a time check, is what we want to do is reverse the concern we have. The concern is having resources that are fully trained and capable of doing troubleshooting. What we want to do is let anybody walk in, click through, and understand what's wrong with their network. So I can answer all sorts of questions related to this afterward. I don't know if you left any time to it. We've got a booth outside. I'll be happy to answer a lot of it. I can give you a little more time showing things. The other thing I was referring to as well is with regards to queries, and this is the last thing I'm going to show, is unhappy clients. So there's not only the concept of, there we go, is the concept of a fault, but then you can have a false positive. You have to correlate what's going on. This is part of the data science bit. So what I can do is I can find different devices are having multiple failures. Only certain devices are having failures which correlate or can clearly be tracked to a specific connection failure for that resource. And this is all about getting rid of false positives. This ties into having a microservices architecture that's capable of receiving data points and having good coding that's built to industry best practices, which will allow you to filter what you need to be looking for and then render it in a UI that anyone can just click through and pull them down. In this particular instance, I could have typed in pretty much any string I want, but I'm lazy, and what I did is I simply just went in and clicked on a specific one that's cached. Once again, that's a cool thing. If you're doing help desk and you got a repetitive task, just show me my common queries and things like that. Here's another example that I'll dig through just for the last second here. This is a particular instance of a watch. The watch was having a whole bunch of different types of problems. When you get a case, if you got a problem out there, it's all about the user experience, right? What's this guy having problems with? They're authenticating okay, but DHC is a problem. There's an alarm on that, but most importantly, what I'm going to do is just go in and investigate certain things. So the support model of the future will be such that you have automatic ticketing systems, which hopefully will automatically resolve things or at least assign them to correct queues, and then I'll have tools which allow me to walk through it more efficiently. So I ran through that rather quickly, but I hope that was great, and thank you for your attention today.